Hello dear students. So far we have discussed the formation of cloud, how the cloud condensation nuclei are important for the formation of cloud droplets, and what happens when this cloud droplet once forms and travels within the cloud, what kind of physical effects can take place, right. We have also seen what are the various different types of precipitation, in the form of liquid water, precipitation in the form of solid ice, so many things. So now when we want to understand the diffusional growth of a liquid droplet, how a small cloud droplet, which is a result of the condensation, grows to be the size of a rain droplet, what are the physical processes? Now, in order to be able to understand these things mathematically, we should consider two very important effects which are called as curvature effect and the solute effect. Curvature effects is important in the sense that the rain droplet is spherical in shape, and being spherical in shape will affect how the saturation vapor pressure changes with respect to plane surface of water, right. Now, just imagine if we consider forces that are holding a water drop together for a flat and curved surface. So we wanted to understand what will happen if you have a plane surface of water and if you have a curved surface of water. So what is the force that holds the molecules, various so many molecules on the surface of this plane surface or inside a droplet. So if we consider the forces that are holding a water drop together, so there is some amount of force which is holding this water drop together. So it's not breaking apart, it's together in the sense it's a single entity. For a flat surface, we can realize that the forces on the hydrogen bonding of the liquid give a net inward attractive force to the molecules on the boundary between the liquid and the vapor. So this is the boundary which separates the vapor and the liquid. So what the idea is that, so we have all these molecules which are attracted by their neighbors and so on and so forth. So the net force of attraction felt by a single molecule due to all other molecule is what keeps this molecule within the liquid and doesn't allow this molecule to evaporate or to leave the liquid surface, right. Now, the net inward force. So now we want to understand what will be the net inward force. Will it be larger over a molecule if it is plane surface of water, or will it be larger if it is a liquid droplet? Okay. So the net inward force divided by the distance, let's say the force per distance, let's say, is called as the surface tension. So which actually holds the droplet together, right. Or you can also surface tension can also be defined as energy per unit area. So this is the surface tension, right. So the net inward force divided by the distance along the surface is called as the surface tension, sigma. When the surface is curved, let's say if the surface is kind of curved, what happens? The amount of bonding, the amount of force that can be felt by a given molecule due to all its surroundings or due to all its neighbors will be less. The amount of bonding that can go on between one water molecule on the surface and its neighbors is reduced. That is what the idea is. So if you form a droplet, any given molecule on the surface which when evaporate contributes to the vapor pressure will experience less amount of force from its neighbors. So it has more tendency that this molecule can escape and form a vapor, go into the vapor phase, right. So this picture indicates the effect. So what you see here is that this molecule, let's say, is bound by all these forces with all these molecules, long range or whatever. But the thing is, so this molecule overall is experiencing more amount of force due to the molecules, other molecules. But when you take the liquid to be in the form of a droplet, not in the bulk or not in the plane surface, you see that each molecule at any given time is of course experiencing lesser force. So, as a result, there is a greater probability that any one molecule can escape from the liquid and enter the vapor phase, right, the molecule that is on the droplet. So, this has the more probability to escape and enter into the vapor phase. So, vapor phase, more evaporation happens, you will realize the saturation to be achieved much faster. That is the basic idea. So, thus the rate of evaporation will increase from a droplet. The greater the curvature. So, if you imagine a huge or larger droplet, obviously the greater are the chances that the surface molecule can escape. Thus, it takes less energy to remove a molecule from the curved surface than it does for a flat surface. Right. So, the point is evident now, right. So, hence the saturation vapor pressure over a curved surface of water would be larger compared to plane surface of water. Why is it larger? Because of the larger evaporation rate, the saturation vapor pressure, the vapor pressure where evaporation is equal to condensation. We cannot comment on the condensation, but given that we have droplets, we can surely say that evaporation is larger. So, saturation vapor pressure will also be larger, right. So, this effect which comes into picture when you have the water in the form of a droplet is called as the curvature. So, curvature effect is eventually the increase in the saturation vapor pressure due to the water present in a drop, in the form of a droplet, in the shape of a droplet. So, one thing we can surely say that saturation vapor pressure increases due to the curvature effect. Okay, this is the conclusion. Now, we can obtain a mathematical treatment for the decreased saturation vapor pressure due to the curvature. Let us see how we can obtain a mathematical treatment for that. Let us consider a small tube of radius r, which is from which we have removed the air, and it is now in a liquid surface. It is immersed in a liquid surface. So, what will happen is, so with time, as the time progresses, water will enter into this tube, and there will be some amount of evaporation, and there will ultimately an equilibrium value is achieved. So, the tube stands in the water, and water has risen to a height h. So, water will rise to a height h. Let us say, so with time, as the evaporation happens, so it will rise to a height h. So, this is the meniscus. So, the meniscus is curved, right. Now, let us say the sigma is the surface tension, that is force per unit surface area, force per unit length, unit surface along the surface, right. And let us say that rho L is the density of liquid and rho W. So, rho L is the density of the liquid or water, and rho V is the density of vapor. Similarly, P L is the pressure of the liquid or water, P V is the pressure of the vapor. Right. Now, what is the volume of liquid? Now, what we are trying to do is we are trying to see how the saturation vapor pressure over a curved surface ES of R. So, what is ES of R? ES of R is the saturation vapor pressure. Now, we see that we are indicating vapor pressures with a small e. We have put a subscript of S indicating saturation, and R indicating saturation vapor pressure over a curved surface. We want to find out how ES of R changes or relates to saturation vapor pressure over infinity. So, the idea is for a plane surface of water, the radius can be considered as infinity. So, we want to see how the saturation vapor pressure changes with respect to saturation vapor pressure over plane surface of water. Now, let us say, so now to be able to do that, we want to find out what is the height up to which this will rise to be able to balance the forces of, let us say, gravity and the pressure gradient. So, this height will tell us how we can achieve this objective, right. Now, let us say the volume of the column of water, is pi r square h, and its weight, and so if this is the volume, the weight is pi r square rho L minus rho v into g, where g is the acceleration due to gravity. This is the weight of the water less the weight of the water vapor it displaces. So, this is this has weight of water less the weight of vapor, because we have a minus, right. So, since the density of vapor is negligible in comparison to the density of water, we can anyhow replace or consider rho v to be approximately equal to 0 in comparison to rho L. So, the weight of the, so now the weight must be balanced by the force created by the surface tension in the meniscus of the tube. So, this weight that is trying to come down must be balanced by the surface tension in the meniscus of the tube. Now, so, the force surface tension is force by 2 pi r. So, the force that we are talking about is sigma times 2 pi r, right. So, let us say here at the bottom of the, so here this is the liquid phase and this is the gas or vapor phase. Let us say the surface is E0, the vapor pressure at the surface is E0, where at the surface, so and vapor pressure at the height of the meniscus is EH. Okay. Now, we know that if we consider the temperature, so the saturation vapor pressure can be simply written in terms of specific volumes and the latent heat. So, which gives the equilibrium saturation vapor pressure variation with respect to the temperature, right. So, now let us say sigma is the surface energy per unit area or force per unit surface length. So, force balance is, so how can you write the force balance? This force has to be equal to mg. So, surface tension is the force per unit length or interfacial energy per unit area of the liquid vapor interface. So, the weight must be balanced by the force created by the surface tension in the meniscus, right. So, if you write this equality between the forces, these two forces must balance each other. So, sigma times 2 pi r, force on the left hand side, is rho L minus rho v times pi r square times h times g. So, which is 2 sigma is equals to r h times rho L minus rho v times g. So, where we can write h is equals to. So, when these two forces balance each other, we will realize the height of the meniscus as rho L minus rho v times g. So, if we neglect the density of vapor with respect to the density of the water, let us say, so we can write, we have written h is equals to 2 sigma by r divided by rho L minus rho v times g. If we neglect, this expression reduces to h is equals to 2 sigma by r divided by rho L times g, or 2 sigma by rho L g r. So, what is r? R is the radius of that particular curvature with which the meniscus is being made. Sigma is the surface tension or force per unit surface length and or surface energy per unit area. Rho L is the density of the liquid, g is the acceleration due to gravity, right. So, this is a very important expression. So, for if you put a capillary tube in the liquid, so this height, the height of the meniscus where the weight is balanced by the surface energy per unit area or the surface tension, the force due to surface tension, this height is given as this. So, we are trying to achieve how the saturation vapor pressure changes. So, we can simply say that the saturation vapor pressure here is Es of R, and here it is not, sorry, so it is Es, Es of infinity it is. So, it is Es of infinity here, and here it is Es of R. We want to find out how Es of R depends on Es of infinity. That is it. That is the objective. So, we can say that this gives the height at which the upward pressure due to the Laplace pressure associated with the surface tension is balanced by the downward force due to hydrostatic pressure, which is associated with the column of the liquid. So, this downward pressure is due to the column of the liquid, the upward pressure. So, now if you keep it, why isn't that the liquid is not coming out of the capillary tube? It's why should the liquid rise to this particular height? Why should it rise in the first place? If it rises, why is it constant at a particular height? Why is it not above, or why is it not below? The question. So, the simplest answer for that is that this meniscus is maintained by a force balance. That means there is a force which is acting downwards, and this force is countered by a force which is acting upwards, right. So, the Laplace pressure is the pressure difference between the inward and outside of a curved surface. So, if you take a curved surface, the pressure difference, so let us say you have a pressure like this and you have a pressure like this. Let us call this as P1 and let us call this as P2. So, the Laplace pressure is delta P is a difference of the inward and outward pressure. Now, when this pressure balances itself with respect to the downward hydrostatic pressure, then you have a meniscus, right. So, basically, so the idea is these two forces balance each other, and we will be able to write an equation for the force balance. So, if in this case what you see is you have so P1 is larger and P2 is of course smaller. So, the pressure gradient is obviously is in this direction, right. So, this is the pressure gradient is in this direction. So, the net direction of force should obviously be in this direction. So, pressure gradient force, because F is proportional to minus del P. So, whatever the gradient, the force should act in the opposite direction. So, this is the force, right. So, this force should now be balanced, because if this is the force, the entire column of the fluid should rise indefinitely and come out of the tube. It never happens. So, this force must now be balanced by the gravity, right. So, let us say, so we will use the hydrostatic equilibrium. Hydrostatic equilibrium is dP over dz is minus rho g. So, for the vapor phase, we can write the ideal gas as PV is rho v RVT, right. So, we can write the ideal gas for the vapor phase as this, right. So, now let us say, now we want to understand how the pressure changes with respect to height, or how the, so on the difference of vapor pressure at a height h compared to the vapor pressure in the water at the base of the tube is approximately equal to the negative of the weight of the vapor over a height h. Okay. So, if it is the case, then we can integrate this equation from, let us say, vapor pressure at the surface to vapor pressure at the height h is dP is equals to minus rho g, right. And from this expression we can write rho v is equals to PV by RVT. So, if we carry out this, we can write integral E of 0 to E of h d PV over PV is equals to minus g by RVT integral 0 to h, correspondence between the pressure and the height, right. So, we can write ln of E of h minus ln E of 0 is minus g by RVT times H, or ln of E of H divided by E of 0 is equals to minus GH divided by RVT. So, the vapor pressure at a height H is equals to, in comparison to the vapor pressure at the base of the tube, is equals to E of 0 exponential minus GH divided by RVT. Right. So, I hope you are getting this. So, we have started the so we just wanted to find out how the vapor pressure here can be related to the vapor pressure here, right. So, this gives the variation of vapor. So, E of H is equals to E of 0 times exponential minus GH divided by RVT. This is what gives the variation of the vapor pressure with respect to height. Now, what is missing here? We do not have the information of the radius of the curvature, because this can be just a height, but until unless you put the at what radius of curvature, things change. So, since the system is in equilibrium, the vapor pressure of the plane surface, that is E of 0, is the equilibrium saturation vapor pressure, which we will write as E of 0 is the vapor pressure at saturation with respect to plane surface of water, right. So, E, if it is in equilibrium. So, this is at any instant. Now, we write it as Es of infinity. So, we assume that there is an equilibrium, and if the equilibrium is persistent, we will write this as Es of infinite. Okay. So, this saturation vapor pressure over the surface of water where the radius of curvature is infinite, right. So, again the system is in equilibrium. If the system is in equilibrium, the vapor pressure at a height H should be horizontally uniform, right. The vapor pressure at a height H must be equal to the saturation vapor pressure over the surface of meniscus, which we write as, so E of H can be written as E, yes, saturation at equilibrium at minus R. Why is minus R? Minus R to indicate the negative radius of curvature of the meniscus, the type of meniscus that we have taken. So, we can rewrite this expression as Es of minus R is Es of infinity times exponential minus GH divided by RVT. Now, from the earlier derivation, we have already seen the height of the meniscus where the forces balance each other was 2 sigma by rho L G R, right. Now, we can use this in this expression, and we can write Es of minus R is Es of infinite times exponential minus 2 sigma by R divided by RV rho L times T. So, exponent is the ratio of Laplace pressure to the pressure the vapor would leave, let us say, if it has the density of liquid. Okay. So, if the radius of curvature, we just have to have a plus in this expression, where, so we can write a generalized expression for the saturation vapor pressure with respect to plane surface of water. So, Es of R with a positive radius of curvature is the saturation vapor pressure over the droplet is equal to Es of infinity over plane surface of water times exponential 2 sigma by R rho L RV T. So, saturation vapor pressure over a curved surface, or say a droplet, would be larger in comparison to the plane surface of water. This expression itself, so this is kind of 1 plus something, right. So, that means that anything will be more than the plane surface of water. So, saturation vapor pressure over a droplet surface will be larger in comparison to the saturation vapor pressure that you can achieve if you have a plane surface of water. So this is the basic idea, right? So in which direction are we have a vapor phase? So in this vapor phase, if there is pure surface of water, we have to understand how the saturation vapor pressure changes. If you have droplets in this, let's say, then how the vapor pressure changes. Now, right, so this is the basic understanding of curvature effect, and this equation is very famously known as the Kelvin's equation. Now, in the formation of the droplet, there are two things that come into picture. One, we cannot take it to be a plane surface of water because it is curved surface. The other thing is that because it so happens that when the droplets are falling, because we cannot constitute a homogeneous nucleation, because homogeneous nucleation will demand 400 to 500% of the relative humidity, where the water will automatically by itself come together and form droplets. We will never experience such a kind of situation. So what it means is that the moment it encounters LCL, hugely aerosol particles are available. So it means that you are adding something to the water. So we have to understand what happens if you add something to the water. What happens to its vapor pressure? Will it increase or decrease? What happens to the saturation? Will the saturation be achieved easier, or will the saturation be achieved later, let's say? Okay. So this is the basic idea. So we will summarize here saying that, so this is the curvature effect, which says that due to the fact that the droplets are in the curved or in the form of a sphere, the saturation vapor pressure will increase because of the ease with which you can detach a molecule from the droplet and make it into the vapor phase, right. So we will stop here. We will continue this discussion by understanding what is the solute effect and how we can derive an expression how the vapor pressure changes in the presence of a solute in comparison to pure phase. So you have a diluted phase, you have a mixed phase where you have some foreign particles inside the droplet which are trying to change the vapor pressures or the saturation vapor pressure, right. So we will continue this discussion in the next class.